Hello, grade 11s. Welcome to today's lesson on the gas laws, specifically the combined gas law. So far we've talked about the works of Boyle, Charles, and Gay-Lussac, and it would be beneficial for us to take a moment to go back and review what these different scientists talked about in terms of the variables that affect gases and how those variables actually affected the gases. So grab yourself a ruler and let's see if we can break down these three different gas laws and compare them. We're going to turn this page into a chart where we compare and take a look at the variables each scientist looked at, the type of relationship that existed between those variables, which of the variables that they assumed was being held constant in order for their law to hold true, and what the formula that they used was given. Boyle, for example, did his work comparing the relationship between pressure and volume. Pressure and volume have an inverse relationship, which means as one goes up, the other goes down. If I increase pressure, there's less volume, but if I give a bigger volume, there'll be less pressure. Boyle assumes that temperature is being held constant in order for this gas law to be true. Mathematically, we express Boyle's law as being P1 times V1 equals P2 times V2. In an inverse relationship, we multiply our variables. Now, in the case of Charles's, we would be comparing volume versus temperature. Volume and temperature have a direct relationship. As the temperature is increased, the volume or space that the particles will take up will also increase. Charles's law assumes that the pressure will stay constant throughout the entire time in order for the Charles's law relationship to hold true. In Charles's law, mathematically, we would say V1 divided by T1 equals V2 divided by T2. As with all direct relationships, we divide. Remember, temperature is always in the position of the denominator in these gas laws. It's on the bottom, and it has to be in the units of kelvins for the gas law to hold true. The last of our three gas laws, Gay-Lussac's law, compared the relationship between pressure and temperature. Pressure and temperature also have a direct relationship. If I increase the temperature that a gas is stored in, those particles will put more pressure on the container that is holding it. This is only true if the volume of the container cannot change. For example, in a hard-sided container, like a settling gas container, or maybe a spray paint can. The formula for Gay-Lussac's law then will be P1 over T1 equals P2 over T2. Again, temperature must be in the units of Kelvin for this gas law to work. Also, watch that our units for pressure are the same in both the first and the second instance. This is a good point to pause this video and copy this chart down into your notes. If we were to multiply all three gas laws together, and then reduce it to its most simplistic form, we get something called the combined gas law. In the combined gas law, we can compare pressure, volume, and temperature as they change all at the same time. P1 times V1 over T1 equals P2 times V2 over T2. By covering up the variable that remains constant in each of the three previous gas laws, you can see where the individual gas laws came from. For example, Boyle's law assumed temperature was constant, and if we cancel temperature from both sides of the equation, we have shown P1 V1 equals P2 V2, you'd have Boyle's law. In Charles's law, where we assumed that pressure was being a constant, we could cancel out the pressures and be left with the Charles's law formula. So this gas law actually can be used to solve any of our equations, but we use it specifically when we have cases of more than one of our three variables changing at a time. Here's a good example of a combined gas laws question. Again, anytime we do problem solving in a chemistry class, it pays to pick up your highlighter and find all the numbers in the question and their corresponding units. So in this question, we've got 2 liters of a gas collected at 25 degrees Celsius and 745 millimeters of mercury. The words "at" and are linking words. It means these three instances will go together. So looking at the units, liters is a measure of volume. This will be my V1. Degrees Celsius is a measure of temperature. That will be my T1. And millimeters of mercury is a unit of pressure. That will be my P1. These are all instance 1 because they are linked by the words at and. The question asks us, what is the volume at STP? Here's a new expression for us. What does STP stand for? STP is shorthand in chemistry, and it stands for standard temperature and pressure. In the gas laws, our standard temperature is defined as being 0 degrees Celsius or 273 kelvins. So here in the chart, we have standard temperature defined as 0 Celsius or 273 kelvins. Standard pressure can come in 3 different units. Standard pressure may be measured as 101.3 kilopascals, 760 millimeters of mercury, or 1 atmosphere. Since our problem is using millimeters of mercury as a pressure, and we want to keep our units the same on both sides of an equation, we're going to pick standard pressure in millimeters of mercury here. 760 millimeters of mercury would be the standard pressure that we choose to use. Because our temperatures have to be in kelvins in all of our formulas, we will use this value of 273 kelvins as our standard pressure. Standard temperature now becomes our T2, our second instance of temperature, and standard pressure will be our P2. What we're looking for is a new volume. Like with any of our problems, you're going to get a mark for writing down the formula. Since this question involves units of volume, temperature, and pressure, we will write down the formula for the combined gas law, P1V1 over T1 equals P2V2 over T2. We will then substitute numbers in place of each variable from the problem. Our first pressure was 745 millimeters mercury, our first volume 2 liters, and our first temperature 298 kelvins. Remember to change this value immediately to kelvins. Our new pressure will be standard pressure of 760 millimeters mercury, and our new temperature will be standard temperature 273 kelvins. We will now want to solve for V2. What will be the new volume? Just like the equivalencies we had before, draw yourself an X through the equal sign. One of the diagonals will have all the numbers on it. The other one will have a variable. Multiply across the diagonal with all the numbers on it. Divide by the remaining numbers. In this case, the yellow diagonal has all the numbers and the green one has the variable. So mathematically, we're going to do this. Following the yellow line, 745 millimeters of mercury times 2 liters times 273 kelvins, dividing by what's on the remaining line, divided by both 760 and then divided again by 298. Multiply across the diagonal, divide by what's left. This allows you to solve for V2, and the value we have for V2 is 1.8. Since the unit on this side was liters, the unit on this side was liters. It turns out that after we have taken this equation and changed both the temperature and the pressure, our volume has gone from being 2 liters down to 1.8 liter. Let's do one more example. A sample of oxygen gas has a volume of 205 cubic centimeters. Now this is volume. We're not used to this formula, cubic centimeters, but it's another standard way of measuring volume. A cubic centimeter, you guys, is the same as a mil. So this is the same as saying 205 milliliters. And we can change it to that if it makes it easier for us. When its temperature is 22 degrees Celsius, degrees Celsius is temperature, and of course we'll change that by adding 273 to kelvins. And its pressure is 30.8 kilopascals. There's my initial pressure. What will be the volume of the gas at standard temperature and pressure? Remember that standard temperature is equal to 273 kelvins. And standard pressure could be measured as 101.3 kilopascals, 760 millimeters of mercury, or 1 atmosphere. In this case, because we're using kilopascals in the first instance, we should pick the unit of standard pressure as kilopascals for our second instance. This now becomes our T2, and this will become our P2. Again, for a mark, our formula P1 times V1 over T1 equals P2 times V2 over T2. Substitute numbers in place of their variables. The first pressure is 30.8 kilopascals. The first volume, 205 milliliters. The first temperature, 295 kelvins. Our new pressure has gone up to 101.3 kilopascals, and our new temperature has gone down to 273 kelvins. Solve for V2. Once again, we're going to draw a crisscross or an X through our equal sign. Multiply on the diagonal with all the numbers on it, divide by what's left. Again, the diagonal that has all the numbers on it is the yellow one in this instance. 30.8 times 205 times 273 divided by 101.3 divided by 295 will result in the answer for V2, 57.7 mils. The units will be milliliters because they were milliliters on the other side of the equal sign. There's a couple of places where you guys will be able to practice this in your textbook and in your worksheets. In the textbook, if you read pages 449 and 450, you will find problems to try on 450 on page 450, numbers 11 through 13. Also, in your green work package, there are 2 combined gas laws worksheets you can work on. These are found on pages 23 through 25 in your green work package. That's a fair amount of work for us to practice, and I'm probably going to allow you guys about 2 days worth of time to be able to work through these problems and make sure that you ask me questions about them. If you're stuck on anything at all, give me a message. I can work through some questions for you and put up a video showing how I've worked through the answers. I'm willing to continue to put up answers to any of the questions you've been having problems with on any of the gas laws so far.